Are you sure you want to start 3 minutes before? You sure want to start 3 minutes? 3 minutes before 11?
Yeah.
When is it scheduled? Oh, okay. Okay, so I want to thank the organizers for this very interesting workshop, and also for giving me such a great speaking slot, which follows all these reviews about cosmic strings, making my job much easier. And also giving my collaborator, Danny Steer, a slot following me, so I can focus on all the fun things and leave all the difficult things to her. But more seriously, I'll be focusing mostly on cosmological implications and even more specifically on CMB signatures of the scaling cosmic superstring networks, while Danny will tell you more about the actual dynamics of these networks. So I'll briefly go over the main observational signatures of strings that are relevant to my talk, even though they've been mentioned earlier this morning. So as you have heard, strings cut a deficit angle out of the space-time. So if you have a straight string, the space around it becomes conical. So if you have two particles moving in parallel on the two sides of the string, they'll start moving towards each other after they pass it. Or if a string passes between two particles, the particles will start moving towards each other. That applies to both matter and photons. So if you had a uniform cosmic microwave background backlighting a cosmic string moving across the sky, then you would see more energetic photons behind the string. So it would lead to such a line discontinuity. Thanks for Paul Shellart for lending me this picture. Now, if you had many strings, you would get a superposition of such line discontinuities. And this assumes that the background CMB is completely uniform and strings are the only source of distortions. Now, in addition to such discontinuities, you also have wakes. So if you have a string, it will move, and behind the string, particles of matter will start moving towards each other, and you'll get enhancements of density, which would be these wakes. And the dimensions of the wakes would be determined by the velocity with which the string is moving, the characteristic length scale of the string, and the tension of the string mu. Okay. Now, combined, these effects would, the line discontinuity effect and the production of wakes together would produce inhomogeneities in an early universe, and in particular at the time of last scattering, and they would be imprinted later in the cosmic microwave background that we are currently measuring. So cosmic strings for a long time, because of these properties that I mentioned earlier, were considered a possible mechanism for generating inhomogeneities that would later grow to form cosmic structures. But that didn't quite work out, because when you look at detailed predictions for example, how the spectrum of the CMB temperature anisotropies would look, it doesn't look like what we measure. We measure this is a very, very old plot. Currently, we measure this to much better accuracy, to much higher Ls. So there are oscillations that we don't see with cosmic strings. For those of you who see such a plot for the first time, what is plotted here is a root mean square temperature fluctuations of the cosmic microwave background as a function of angular scale. So on the right, you have smaller scales. On the left, you have larger scales. So cosmic strings are not needed to explain the cosmic microwave in any way, but they can be tolerated. In other words, you can add a cosmic string component to your model. So you would have inflationary perturbations. You add some contribution from cosmic strings, and they would not destroy your fit if the contribution doesn't exceed 1 or 2%. Now, this measurement of the cosmic microwave background, especially of this first peak, happened in year 2000, where two suborbital experiments, Maxim and Boomerang, measured the first peak. And that already ruled out cosmic strings. That's why there was a dip in the number of papers written about cosmic strings. So the interest dropped sharply. But then it scrolled back. And so Anna Chukar earlier today mentioned why that happened. Well, one reason is that there are lots of people who really like topological defects, and including people in this room. So one way or another, we find problems that we can solve that have to do with defects. Another reason is that, yes, inflation won the debate as for the primary source of fluctuations, but next step would be to embed the inflation into some particle theory connected to the rest of the physics. And typically when you try to do that, you get additional scalar fields. And often they conspire to break a U1 symmetry and form line defects, so such as models that Anna mentioned earlier. And if I want to be completely honest, the main reason for this jump was actually due to string theorists who also at about the same time realized that cosmic strings can be cosmic superstrings. In other words, superstrings, fundamental objects of string theory, can actually have cosmic size. And there is a link between these two things, namely the context in which this first appeared was in the context of brane inflation. And brane inflation is a type of hybrid inflation, a multi-field inflation model. So there is this connection between the two. So let me give you a sketch for how this F and D strings, cosmic superstrings, can be produced in this brane inflation. I don't speak string theory, but fortunately, Gerd Valiant, Alex Vilenkin translated this into sort of normal language, so I can understand it. And the understanding comes essentially from collision of higher dimensional defects and lower dimensional defects forming as a result of that collision. So you have a D3 brane and a D3 anti-brane. Each of them has a U1 gauge field living on them. Now, inflation happens as these branes move slowly towards each other. And then it ends, and branes annihilate. So this annihilation is described as a tachyonic scalar field, a scalar field, which is complex scalar field, acquiring a vacuum expectation value. It couples to one combination of this U1 field, this minus combination. So when this U1 is broken, you form line defects, which are identified as D1 branes. The other combination is not spontaneously broken, but it has nowhere to go because the branes no longer exist. So it becomes confined to flux tubes. So they become identified with these F strings. So in this kind of models, you form two types of strings, not just one, but two. And moreover, it's not just, you don't get one winding of each. You can have combinations of D and F, and each of them can have multiple windings. So it's a whole hierarchy of strings. So you get this multi-tension string networks of types FD, FD, FFD, etc. It's a whole sequence. And they can differ, F and D differ in the way they intercommute. They intercommute with different probabilities. And these networks have new type of features, such as junctions. They can meet, join, separate, etc. So Danny will tell you more about such properties and specifically about junctions. I'll move forward. So I told you that strings are at best tolerated. So why did string theorists get so excited? Is there any reason to be excited when strings are practically on the verge of being ruled out? So it turns out that even if you don't look at gravity waves or other very powerful probes of cosmic strings, even if you just stick to CMB, there is some hope, and the hope comes from the B-mode polarization. It was realized as early as 1997 that cosmic strings and defects more generally can be a very bright source of the so-called B-mode polarization. So let me tell you what that is. So CMB polarization is a polarization of electromagnetic wave. So that, you say, it comes to us along Z direction. So you measure X and Y components of the electric field for some time, take time averages, and evaluate the Stokes components, intensity, Q and U, which are the two numbers quantifying linear polarization along that one line of sight. and the circular polarization that you don't expect because Thomson scattering doesn't produce it. So you can combine these numbers into magnitude of the linear polarization and an orientation angle. So it's a headless rod. It has no direction. And then you can actually represent it as a picture, which would be your map. So this is the first measurement of CMB polarization done in 2002 by Daisy. The colors are the intensity fluctuations. And little rods quantify the lengths of the rods quantify the strength of the linear polarization, while the orientations are given by that angle alpha. So it's become traditional, rather than working with the Stokes parameters Q and U, further decompose them into particular types of patterns. So there are two types of patterns, E and B. They get their names from analogy with electromagnetism. So E modes would be things you can get by taking gradients of a scalar. So they expect it to be there and have been measured because we had density fluctuations. Now B modes, on the other hand, don't need to be present. There's nothing in our existing model that says there must be B modes. And for that, you need some additional physics that would have fluctuations of handedness, something that would have left or right-handed components, such as gravity waves, magnetic fields, and in our case, anisotropic stress from defects. So defects are very good at producing vorticity fluctuations, and it's not just vortices, it's more of shearing. It's an anisotropic stress producing shearing, which introduces a vorticity field. So the B mode from strings would look like this. To give you a perspective, again, this is L, the angular scale. These are small scales, large scales. This is the scale corresponding to the horizon at last scattering. And this is the prediction of inflationary B modes with some optimistic amplitude. This is a prediction. The very faint dotted line is the foreground lensing, which changes E mode into B mode. It's essentially expected because gravitational potentials along the line of sight introduce additional distortions to the polarization. And the red and blue lines are cosmic string signatures for a couple of different models. Okay, so they can be fairly bright. Now let me now tell you how we calculate such things. So CMB from strings is very complicated, as some people in this room know very well. And I admit that we have probably the simplest and least sophisticated approach to it. But in many circumstances it works. So the idea is that you start with a wish that all the properties, or most of the properties of such spectra would be determined by some basic characteristics of your network, such as correlation length and velocity. So if you ask what are the ingredients for it, so expansion stretches the string, so it increases total energy in the strings. And they reconnect and chop off loops, so they lose energy. Combined, that results in a scaling solution where you have roughly a fixed fraction of total energy in the universe bank in cosmic strings. There have been models developed to model such a scaling solution, starting with Tom Kibble, who had a model for the energy density in strings, rho. Okay, this has two terms. Expansion stretches them, loops decrease the energy. This is called one-scale model because you can define a length L related to rho in this way. So it's one scale, a length scale, that you can define as giving this rho. And Carlos Martins and Paul Shellart extended this model to make it more flexible. And they've included an equation for velocity, and they've included these additional parameters that can be adjusted to match real simulations that they've been doing. So what we do is we use this one-scale model as an input into the so-called unconnected segment model, which Mark Heinmarsh mentioned briefly. It's based on modeling of strings as unconnected segments. Again, the idea first came from Heinmarsh and Mary Saccolorado and others, and then we took that over from Richard Buddy and others. So Tanmay and I, when I was a student, wrote this code called CMB Act that allows us to calculate CMB given this velocity-dependent scaling model parameters. So I'm not going to go into this too much. Instead, I'll tell you what do we do next. So we want to calculate it for multi-tension strings. So we extend it. Now we have several types of strings, in fact, an infinite hierarchy of them. Each of them has a tension. The tension, if you know, depends on two fundamental parameters, the fundamental string tension and the string coupling GS. And all I want you to note at this point is that when GS is very small, the mass of the D string, which is given by Q charge, becomes very large. So small GS makes D strings very heavy. So P and Q are integers. It's a hierarchy of integer numbers. And then but Tassos Avgustidis and Ed Copeland wrote this model, which now allows for much more complicated dynamics and relationships between these different types of strings. So these coefficients here depend on properties of junctions that Danny will review for you. So what do we find? We do find scaling solutions in this model, and scaling means that this length scale would actually go as a constant fraction of this physical time t. What we find is that the lightest strings, which are always the F strings, are always the most popular, which is not very surprising. However, what's interesting is that if you ask what determines the CMB normalization, which type of string will make the strongest contribution to the CMB, it turns out that when GS becomes very small, this mu becomes very large for them, and it overwhelms the fact that they are rare. So at smaller couplings, your CMB is dominated by rare and heavy strings, while at larger couplings, it's dominated by lighter and popular strings. And that suggests that there may be an observational signature to it, such as in our case, what we looked at is the change in the peak of the B mode. So we saw that depending on the string coupling, the B mode peak shifts. And I will unfortunately have to rush a little bit and just tell you that so we asked how well such a shift can be measured. So we don't just ask how well strings can be detected through B mode, but also how well you can resolve a peak. So on this axis, we have the fraction of strings contributing to temperature anisotropy. So the current bound is about 0.02, somewhere here. These are different types of experiments, and since most of you are theorists, let me just look at Planck and the most optimistic case. So Corey would be the future hypothetical dedicated satellite, while Planck is next door. I mean, it will happen soon. And so you can see that you can detect B modes from strings even if they contribute at 0.01%, so 10 to minus 4 fraction, with something like Corey, a future satellite. Even with Planck, if it happens to be right at the current bounds. But yeah. Now, if the fraction in strings is less than, if at about 0.1%, you can actually resolve the difference between peaks. And unfortunately, Tanmay is on his feet, so you can ask me more about this. The bottom line is that you can do it. And final thing I want to say is that there is this trade-off between number of strings and their mass. So when you see something on the sky, it doesn't just give you a constraint on G mu. It always constrains some combination of number density and string tension. And different observables depend on those in different ways. So in particular, gravity waves constrain density. CMB constrains something else. And if you combine them, you can actually partially break some degeneracies between your string parameters. And this is my summary. So strings are practically irrelevant for temperature anisotropy. However, they can still be a very powerful B mode source. Measuring the peak of the B mode is possible, and it will constrain some fundamental physics. And further, you can combine different probes to break degeneracies between number density and string tension. So thanks.
May I just ask Carlos to set up? Any questions for Levon? Yes, please.
You may have said this and I missed it. Is it the case that statistically, if you statistically analyze the background radiation in terms of all 6 Stokes parameters, you see deviations from what you expect as deviations from mean. And we know that the density, the intensity does have that, but does polarization deviate from an average random?
So polarization is not very well measured yet, but from what has been measured, it looks very much like what you would expect from inflationary prediction. So it doesn't look like cosmic strings are needed so far.
Or anything else, or anything.
Well,
If there
as
are
far as I know, there is. I mean, as I said, it's a very young field. There is practically not much information about polarization at this point.
Thank you.
Let's thank Levon.